Hello, Tech World. This is Tech Thoughts. In this three-part video series, I'm going to be exploring the topic of subnetting. When you've completed all three videos, you'll have an understanding of what subnetting is for, and you'll be able to properly calculate subnets. While there are calculators out there that can perform subnetting for you, this is still a great skill to have in any IT position. This is the first video in the series, binary conversion. Let's go ahead and get started.
All right, so today we're going to be talking about binary conversion. And binary conversion is extremely important because this is your very first step on learning how to properly subnet. If you can't master step number 1, binary conversion, then you can't successfully go on to learn how to properly subnet, which we'll be talking about a little bit later. So let's talk about what binary is. You probably know this already as ones and zeros. Fundamentally, at a basic level, this is all your computer, your smartphone, or your laptop is capable of understanding. Something is either represented as off, a 0, or something is represented as on, represented by a 1. It's as simple as a light switch, and that's all your computer is capable of doing. It's crunching a lot of binary information, ones and zeros, which ultimately makes up a picture, a video recording, so on and so forth, a YouTube. It's all at the basic level, a 1 or a 0. So that gives us two choices, a 1 or a 0. And because we have two choices, 2 becomes a very important number in binary conversion, in binary itself. So you may have heard something being 32-bit or 64-bit. And have you ever asked yourself, what is the difference between those two? And what it has to do with is we have two choices times the power of 32. This is 32-bit. Or we can say we have two choices to the power of 64-bit. So let's talk about this. We know these as exponents. Let's talk about how exponents are important to binary conversion. So at the basic level, we can start all the way back at the beginning, and we can say 2 to the 0 exponent is, of course, anything to the power of 0 is 1. We can go 2 to the 1, and we get 2. We can go 2 to the 2 and get 4. And just to break this down a little bit further, when I say 2 to the power of 2, what I'm actually saying is there are actually two 2's. So here's the first 2 times the second 2, 2 to the power of 2 equals 4. So moving on, we get 2 to the third, which is, of course, 8. 2 to the third is 8. And what that's saying is 2 times 2 is, of course, 4 times another 2 equals 8. We're essentially just adding another 2, giving us 8. 2 to the fourth, 16. 2 to the fifth, 32. And what I'd like to point out here is because this is two exponents, we are actually doubling each time. 2 to 4 to 8 to 16 to 32. So even if you didn't have all this memorized, you could say right now 2 to the 6th, 32 doubled is, of course, going to be 64, and 2 to the 7th is going to be 128. And what we end up with here is a really nice table, what I like to call the table of 2's. And that's what's represented here is the exponents of 2 all the way up. And what we end up with here is we actually have 1, 2, 3, 4, 5, 6, 7, and 8. So this is an 8-bit system. We have 8 bits to work with. And let me talk about that a little bit. So we have 2 to the 8th. Now you may not see 2 to the 8th here, and let me explain a little bit about that. So we have 2 to the 8th, which is going to be 256. Okay. Now, although you don't see 2 to the 8th here, if you were to take 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you end up with 255. Now you may not be saying, I'm confused now because 2 to the 8 is 256, whereas if I have a total of 8 bits, remember, because 0 counts, 0 counts. Again, 0 counts. So what we actually have here is 0 to 255. So all 8 of these bits total up to 0 to 255. And because 0 counts, this is actually a total number of 256, which is confirmed to be an 8-bit system, which is what we're working with here. So let's relate this to how binary functions in the real world. So here we have, of course, Mario. And this is on their first Nintendo that was released in the early 80s. And the first Nintendo that was released was 8-bit. Now, what does this mean? 2 to the 8th, 256. So that means we have an 8-bit system and 256 different options. So let me explain this a little bit. If I'm to take something and say 2 to the 1, this is a 1-bit system. 2 to the 1. 2 to the 1 is 2 options. So in a 1-bit system, I have 1 bit to work with. This 1 bit can be a 1 or a 0. The reason I get 2 options is because with that 1 bit, I can make that a 1 or a 0. Gives me 2 different options in a 1-bit system, 2 to the 1. So let's take this and add a little bit of complexity. And let's work with a 2-bit system. So in a 2-bit system, I know I have 2 to the 2, this is 2-bit, and 2 to the 2 gives me 4 options. Now because this is a 2-bit system, I have 2 bits to work with. Now these can be either a 1 or a 0. Again, 2 bits to work with. Again, 2 bits to work with. And finally, my last option will be a 0, 1. So in a 2-bit system, I get 4 options, 4 different options here. 4. Now, in an 8-bit system, we get a lot more complexity. 256 options, and obviously I can't write all that out right here, but you get the idea. With 256 options, I get 256 different colors, 256 different enemies, 256 things to work with, which gives me this level of complexity for Mario. Now, when we ratchet that up to the next generation, we go to Super Nintendo. And Super Nintendo was 16-bit. So that's 2 to the 16th, 16-bit, which gives me 65,536 different options. And with this increased level of options, I'm able to make a more complicated Mario. Now we come to Nintendo 64, which you might guess is called that because it is 2 to the 64th power. So 64-bit gives me 2 to the 64 this number, which is 9,223,372,336,854,775,808 different options. That many choices of ones and zeros. This allows me to make a much more complex graphic environment, and Mario got a huge facelift for Nintendo 64. Now with this number of options, when we went up to the Wii, so this is the Wii, we still didn't need to increase our exponent level, our number of choices. This is still, the Wii is still 2 to the 64, we're just getting better at designing. But we still have the same number of choices. So all we're talking about here is the number of actual binary choices based on the number 2, because that's how many choices we have. And we basically have gone through some iterations here. 2 to the 8th power, which is 8-bit. Here is 2 to the 16th, 16-bit. And then now today we are at 64-bit. So let's talk about how this works and how we can use this table of 2s and choices to convert binary to conversion now that we're done with that brief introduction about how binary operates. So let's take the number 4. This is a decimal number, and I want to convert it into binary format. So how many places does this fit into? Now remember, because this is an 8-bit system, I have 8 different choices. Each one of these is going to be a 1 or a 0. And we have to make a determination about which one is going to be which to do this conversion. All right, so we're going to go from left to right, just like you're used to reading. So left to right. And we're going to say, can 128 go into 4? Can this number right here go into this number? And the answer is no. So this is going to be a 0. We made that decision for our binary conversion. We're going to ask the same thing for 64. 64 cannot go into 4. Neither can 32. Neither can 16. Neither can 8, because it's too big. However, 4 can go into 4. So we're going to put a 1 here. And we've added 4. And this leaves us with 0. Because we have nothing left to work with, we know that these last 2 numbers are going to also be 0. This is the binary representation of 4, this right here. It is customary to cut out the zeros. So all those leading zeros, we'll ignore those. And we can say 4 in binary is equal to 1, 0, 0. Okay, so let's do another example, and this time we'll make it a little bit more complex. So we'll say, what if we take the number 7, which is a decimal number, and we want to convert this? And again, this is an 8-bit system. We have 8 different choices that we have to make, either a 1 or a 0 in each of these. So, can 128 go into 7? Of course it cannot. Neither can 64, neither can 32, neither can 16, neither can 8. But 4 can go into 7, so we're going to put a 1. Now, we took away 4. This leaves us with 3. Now, can 2 go into 3? Of course it can, so we're going to put a 1 here. We have now added a 2. This leaves us with 1. And our last number is 1. So the number 7, and remember we're going to ignore all the front zeros, can be represented in binary as 1, 1, 1. Now, on the flip side of this, to prove that we are right, if we take these numbers here, so we have this turned on, the number 4 is turned on, so 4 is turned on. If we take the number 2, which is also turned on, and we take the number 1, our final turned on number, and you add 4 plus 2 plus 1, this equals our decimal number 7. An excellent way to check your work. All right, so let's do another one. We'll do a little bit bigger this time, and we'll say the number 25, our decimal number. All right, so again, we're working with an 8-bit system. And we're going to try to determine what the binary conversion for this number 25 is. So can 128 go into 25? No. Can 64? No. Can 32? No. But 16 can go in here. So we're going to put a 1 on 16. We have taken away 16 from this. And so doing normal subtraction, you get 9 left over. And so can 8 go into 9? And of course it can. You've taken away 8. And this leaves us with 1. And because you know that 4 and 2 are not going to go in here, you know that this is going to be 1 left over here. So the number 25 can be represented in binary, and ignoring these front zeros, as 110001. Now, to check our work, we can add 16 to 8 plus 1. So 16 plus 8 plus 1 equals, of course, 25. So now let's do a reverse number. What if I gave you the number 1, 0, 1, 1, 0, 0, 0, 0? Can you convert this to binary? Of course you can, very easily. We know this 128 is turned on, plus 32, plus 16, plus, and we have nothing left here, so this is all blank. So we have 128 plus 32 plus 16. So we just add 128 plus 32 plus 16, and we get the number 176. So let's flip that around. We have a decimal number 176, and we'll go ahead and erase all this just so you can see it done the other way. So 176 is our decimal number. Now, can 128 go into 176? Of course it can. So we've added 128. And that, of course, is going to be 48. This cannot go into, 64 cannot go into 48. However, 32 can. That leaves us with, so we're going to subtract 32 here. And that will leave us with 16. Now we know 16, of course, goes into 16. This leaves us with nothing. And of course, you know, because we have nothing left, that all of these are going to be zeros. Now, because this has a leading 1, we have nothing to ignore. So you must write out the number as 1, 0, 1, 1, 0, 0, 0, 0. Trailing zeros are never ignored. Only leading zeros are ignored. Okay, so let's do one last example for our binary conversion. We'll say the number 128. Now, this should be extremely easy. And by looking at your table of twos, which you should, of course, at this point, have realized you must memorize this. Very easy to do. Our decimal number, 128. And does 128 go into 128? Yes, it does. This leaves us with nothing. And so you know that all the rest of these will be zeros. So 128 written in binary is 1, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, and 8. All right, so because we're using an 8-bit system here, 8 choices, a question I could ask you is, what is the biggest number we can make here? I mean, we only have so many different possibilities. And even if I turn all of these on, and I add 128 plus 64 plus 32 plus 16, 8, 4, 2, and 1, the biggest number I can make is 255, which is kind of limiting if you think about it, because we obviously want to work with numbers with our computers that are bigger than 255. So I always need to start adding numbers here till I got to a point where I had enough numbers to work with. And today's computer systems are generally 2 to the 32, 32-bit, or 2 to the 64, 64-bit. So the two takeaways I want you to take away from this lecture is, what is the purpose of binary and why you sometimes see things like 32-bit and 64-bit, and also how to convert decimal numbers to binary.
If this video was able to help you out, go ahead and click that like button and subscribe for more Tech Thoughts videos.